Righto, welcome everybody. And today I'm really super excited to present to you some work that has been done by NVIDIA, UPenn, Caltech, UT Austin from an amazing, fantastic set of authors, which is titled Eureka, Human Level Reward Design via Coding of Large Language Models. So the way I like to think about it is this is like designing rewards for reinforcement learning via GPT-4 LLMs. Um, this is very exciting work. I mean, it blew my mind when I saw it. It is a 2023 work, so it's relatively fresh. And yeah, I want to talk to you about why I think this work is like super amazing. So the story starts as any other reinforcement learning story, where we have an MDP which we would like to solve. And that MDP is composed of a state space S, an action space a transition model P, reward function R, and a discount factor. The state space is where the agent is. The action space is what actions are we going to take in the environment. The transition model tells me how the environment behaves depending on my action that I applied in a certain state. Where do I go next? And the reward function tells me how well my agent is doing towards a goal that I have encoded through a reward. Okay. The standard RL loop happens, right? So the idea is that you have the agent, talks to the environment, applies action, environment responds by successor state and a reward. And the goal of the agent is to find that policy, right? That policy pi, that action selection rule that will maximize the total rewards you would get from the environment. As we said last time, Richard Bellman and Rich Sutton were one of the, especially Rich Sutton was the person who popularized RL in the world of AI, and please buy his book, which is Reinforcement Learning Introduction. That's the one you would see here. Okay. Now, although reinforcement learning actually worked, the question was, what are we gonna do about those rewards? So for any RL practitioner, if you're an RL person, RL engineer, RL researcher, you know that the most tedious task, the most annoying task you can do in a reinforcement learning solution or algorithm is to code the damn reward functions. How you engineer those reward functions dictates how well your agent performs. It is very difficult to get the right reward that actually dictates what we want the agent to do, takes into account all the possibilities that can happen. And it's the most critical component of reinforcement learning. If we specify the wrong goal, the agent will learn nothing. So here are some examples. You could design rewards that will allow a cheetah robot, to run like this, right? So this is a cheetah robot running forward with a reward saying, okay, run forward as fast as possible. But at the same time, because you didn't take into account all the intricate properties of your simulator, the cheetah robot can still learn a policy that does this. So it'll flip on its head and it'll just try to continue moving forward, right? So yeah, sorry, my computer is a bit slow, but the idea is that, as you will see, hopefully in this video, the cheetah robot flipped on its head and it actually continued to walk forward, getting positive rewards, albeit an unsafe behavior, to say the least. But because we didn't design the reward in such an amazing, correct way to take into account all these things, you can get behavior that look like this. Apart from this, another, and also please note that I got those from this awesome blog. Please go ahead and have a look at it. They have really amazing stuff happening on these reward designs. But another problem, right, which is maybe also critical or maybe even more critical in reinforcement learning, is the sparsity of the reward signals. So in reinforcement learning, all the learning signal is coming through a reward value that comes from the environment. The problem is that in many cases, this reward value is actually sparse, which means that there's not much supervision to do correct credit assignment or correct learning when you are doing reinforcement learning algorithms. So here I show you an example of a very famous problem in reinforcement learning. I think this was one of the hardest Atari games to solve. It's called Montezuma's Revenge. The idea in Montezuma's Revenge is that we have this dude, this player, and this player needs to go down the ladder, jump on the rope, go down the other ladder, jump over the skull, go above, go on top of this ladder, get the key, come back, open a door, go to the next level. Now, the problem is if you take any mistake, if you make any mistaken decision, you will see that you will die a lot and you will get no reward. The only time you will get the reward is at the end. If you're able to get the key, come back and open the door. So in other words, you make so much trajectory, even maybe very long ones, because you might have been able to jump over the skull, but you die here, let's say. And you're getting zero rewards everywhere, and maybe towards the end, you're getting a reward RT, making this reward very, very sparse, therefore offering negligible supervision for your RL agent. So therefore, if you train on this, it might not work, it might take so many trials, and it will still fail. So this is a very old problem. It's not a new problem. And this problem has actually been studied in the reinforcement learning literature for a very long time. So we have methods that are curiosity-driven based to improve exploration. We can design curricula in order to improve the way the learning happens, or we can add auxiliary tasks as well to even improve exploration further. If you're interested in those techniques, there's an amazing blog called Reinforcement Learning Dealing with Sparse Reward Environments by Karam Daboul, I believe. And please do have a look at it. I think it's really fantastic. Okay. So now, those methods, right, they kind of worked. It's not like they didn't work. They kind of worked. So, for example, there was this amazing paper by Belmar et al. From DeepMind. And then they were able to show, that if you actually apply those things, apply intrinsic motivation-based, curiosity-driven based exploration, you are able to actually, go deep in this Montezuma's Revenge game, and you're actually capable of solving the Montezuma's Revenge game, going to, very deep levels in this game. So it actually works. So albeit that the reward is sparse, if you are smart in the way you explore, right, then you are actually capable of doing well. However, what is the problem with these methods? So while these methods are actually, good and useful, they really need a lot of domain expertise. I mean, if you read those papers, they are not, let's say, the easiest papers to understand. They are fantastic papers, great discoveries, but you have to be a domain expert to really understand, what is going on and how would you apply those techniques inside reinforcement learning. Also, while those are true, you still need to design your task specification very, very carefully. So the design of the rewards has to be very, very careful to give us some, reward or learning signals. And really, it's not very easy to take those from Atari games, and put them on, for example, dexterous manipulation, complex robotic tasks. If you would like to actually understand the problems, right, of the reward of these methods, let's say, or reward design, there has been a very, very, very nice paper, right, from Bosch, University of Texas at Austin, MIT, and Google Research and Sony AI that actually tells us a bit more about, this trial and error manual reward design, which we do, and it actually shows a lot of overfitting and invalid task specifications. Actually, I think over 89% of the people reported that they actually do, manual reward design, and they believe those reward designs are actually not optimal for the task. Please don't take these numbers with a grain of salt. I think read the paper; they have the right numbers. It's just from memory. Okay. So now, albeit we've done, so much good research, right, in trying to improve this sparsity reward problem and, automating the reward design, we still have some problems. As we said, we need to be domain specific, we need to design rewards carefully, and we cannot really just rely completely on exploration because, if you want to do that, then how can you apply it on the real robot? Right, so now, how can we automate this process, right? Can we come up with something that will allow me to do better in solving these problems? And in doing so, well, can I rely on the latest discoveries I've made? So for example, can I rely on something like a large language model to do that. So let's think about what we really mean by this, yeah? So instead of really, dealing with all those problems manually, what if I somehow automate a process where I go to the environment, do something, get some feedback from the environment, and ask a sort of a smart model to generate new rewards for me? I try them again, and then I repeat this process. And that's exactly what Eureka has done. So fear no more, because Eureka has actually resolved some of those problems for us. So the way Eureka works is like this. So you have a coding large language model, which is a GPT-4. I mean, you could use other models, but I think this needs further testing. You will provide to this model the environment code. So you'll provide it with, what the environment looks like. For example, the object pose, the rotation, and the fingertip state, and so on. You will also provide it with a task description. So, for example, what they wanted to do is they wanted to make the shadow hand spin, a pen. Then you would go to GPT-4, and then you would ask GPT-4, okay, design for me a reward code, right? You will say, okay, here's my reward signature function. Please provide for me, what your reward code should look like. And then the GPT-4 will sample from its posterior, right, in an autoregressive fashion, a code, right, which is a reward-based code. Then the paper, what it does, the Eureka paper, is that it goes to Isaac Jim, right? And then it applies a reinforcement learning method on top of the reward function generated by GPT-4 automatically. Then it will get a fitness from the environment, how well it had executed the task, and then it will reflect on that reward so that the LLM, the GPT-4 in this case, could yield better reward functions, and this process repeats. So it's really simple, right? I mean, it's relying on how good large language models are, admittedly, but it's really cool because all you need to do now, you don't really need to be a big domain expert, right, to design these rewards anymore. You just need to provide the environment code and also a task description. And then the GPT-4 will generate the code for us, go train, and then after you train, it does a reflection step. The reflection step will be something like, we trained the RL policy by the code you gave us, and here are some of the parameters you gave us. Carefully analyze that and give me a better policy, and then repeat this process over and over again. What is amazing, right, is that they were able to show that with not a lot of trials. So this is also what's critical. They were able to show that with maybe 16 trials, you start getting very good behavior. Very successfully executable reward functions. And they tested that on many domains, 9 tasks from Isaac Jim, 20 tasks on dexterity, and very fancy stuff with the shadow hand spinning a pen. Okay. Right. So that's the idea of the Eureka, right? So the whole idea of the Eureka is, as we just said, take the environment code, with the task descriptor, pass it to the coding LLM, reflect, repeat, and so on. Now, what is super cool, I believe, about this as well is that in our tests, I don't think you need the full environment code for this to actually work. You need more like a specification of the state variable, and then it can actually work relatively well. Okay, so this is super cool. What did they show in the paper? So as I said, they took these set of tasks from Isaac Jim 9 tasks, from dexterity 20 tasks, from pen spinning, with a shadow arm, a shadow hand. And then they had 3 baselines. One baseline was the sparse reward from the environment. So whatever the environment is doing, just the sparse reward. The other one was a human design reward. So us sitting down and designing what we think good rewards are. And a similar approach, which is called language to reward robot skill synthesis, which was done by DeepMind. And here are the amazing results they have. What they were able to show is that, first of all, Eureka, which is this blue bar here, and that's the success rate, was able to achieve 55% success rate on these 20 dexterity tasks, compared to 24%, 24.4 for the L2R, which is the DeepMind approach, compared to 45.9 for a human. So we're not that bad, actually, but, we can do better. And of course, only getting 10.4 for the sparse rewards, which is like kind of the worst solution. And now they also tested this for human normalized scores across different tasks like cart pull, ball balance, quadcopter, Franca kitchen, and humanoid, animal, shadow hand, and so on. What you can see is either Eureka is doing as good as the baseline in low dimensional domains. However, when we go to high dimensional dexterity domains, the Eureka is getting a much greater result. So the method actually works. The idea of providing or generating autonomously a reward function via GPT-4 in this instant, it actually works. It's fantastic. But what it could do is something that is just extremely impressive. This task is the result of the Eureka function with an RL policy to spin a hand. And what you can see, to spin a pen, sorry. And what you can see is that it's actually capable of spinning the pen. I mean, I would have had an extremely hard time in designing such a reward function manually. But using the priors embedded in GPT-4, Eureka was able to do that. This is just impressive. Right. So with this, I would like to end with a couple of words on Eureka. So first of all, we have reviewed the importance of the designing the reward function for reinforcement learning. And we actually said that if you have a bad design or a wrong design of a reward function, you can get crazy behavior. Remember this cheetah flipping on its head and just moving forward. Or if it's too sparse, it's also hard to learn, as we saw in Montezuma's Revenge. So while we have devised many solutions that are capable of handling this, like, for example, based on intrinsic motivation, curiosity, curriculum learning, or auxiliary tasks, those are still tedious to apply because we need to be domain experts to be able to do this. So then what we have been able to then achieve is a Eureka algorithm, which just takes the code of the environment, takes the description, natural language description of the task, asks GPT-4 to generate for it a code, which is like a reward function code. And then that reward function goes to an RL algorithm. The RL algorithm learns, it gets fitness from the environment. That fitness from the environment is reflected in the next iteration of calling the GPT-4. So when I say reflected, it's exactly this reflection prompt, right? Which is saying, that's what we've tried according to what you said. It didn't do well. Can you do something better? Analyze carefully. Can you do something better, right? And then this actually led to amazing results, varying from things like simple card pulls to spinning pens in dexterous manipulation. The code is open sourced, I believe, and there's much more cool videos, right, that you can actually have a look at here. Now, what are the problems with this method? Okay, so there's easy problems to see, and there's to solve, and there are a bit harder problems to solve. First of all, I think they heavily relied on GPT-4. For this method to work well. Now that could be expensive, although they don't do much calls to the API per, a robot or a task. But of course, if you have a lot of tasks, then you spend a lot of money. So the question is, could we, as a community, regenerate those results, right, effectively using latest advances in open source models, right? And if so, do we need to fine-tune those models, right? What does fine-tuning those models, those open source models, actually give us extra on top of using like a general model like GPT-4? Maybe it will reduce how many times we need to interact with the environment. Two, which I think is a more interesting question from my point of view, and that question is, Eureka works fine, but it really needs to know the state variables, okay? It really needs to understand the state variables. Now we see that robotics, right, with all the amazing work Google is doing and other companies are doing, is actually becoming vision-based control, right? So we're kind of controlling from vision. So of course we can from vision, have a pipeline that will extract those features and so on. But the question is, can we enable a Eureka style learner, but actually from vision? So here we don't need anymore things just that are large language models. Here, vision language models become and play a role. So how could we get this, to work well? So these are very exciting questions for the future. I think that if somebody's interested in, please comment or talk to me. However, going back to this amazing paper, I think thumbs up, thumbs up. It's amazing. It's really cool. Amazing set of authors, amazing work, amazing results. The only problem is, of course, it's GPT-4 based, so I don't know if it's easy to rerun your algorithm. So yeah, so that was this paper. Please follow me on HBO Ammar on X, changed it from Twitter, and or follow me on LinkedIn at Haytham Ammar. With that, I would like to end this talk. I hope you enjoyed it. If you did, please like the video and subscribe to the channel so that we can keep making such videos. So with that, I would like to thank you, and I will see you next time. Thanks.